welcome back. We are nearing the end of this portion of our discussions of acids and bases. We'll deal with weak acids and bases later on in the semester. For now, let's refresh our memory on how to write a neutralization reaction. Sorry, I missed these. Let me fill this part in for you. When an acid and base react together, they will always form an ionic salt plus water, and it's called a neutralization. We're going to be looking at full neutralizations, and the ones we'll be doing are straightforward double replacement reactions. So let's refresh our memory on how we did those. So we had H2SO4. Now, any acid plus any base, weak or strong, will go 100% to product until one of them runs out. Now, this is the positive, this is the negative, this is the positive, this is the negative. Remember, this positive will go with the opposite negative, so I'd get HOH or water, right? That leaves the K plus to go with the sulfate, so I'd get K2SO4. And I need to balance that with a 2 and a 2. Let's try our next one. Calcium hydroxide. Boy, if you don't know your polyatomics, we're in big trouble. Phosphoric acid, it came from 8. Phosphate is -3, which is why I need the 3 positives to balance. -1 plus 2. So remember, they trade dance partners, always making sure that positives go with negatives. So I'd get calcium, but don't look at those subscripts here when you're doing this trading. Look at the charges when you're doing your trading. So calcium dances with phosphate, the lowest whole number ratio, the least common multiple is 6. So I need 3 calciums, I need 2 phosphates, and I get water, salt plus water. So now I have to balance that. I'd need a 3 here, a 2 here, and a 6 there. Lithium hydroxide, us came from ite. Chlorite is ClO2. So that was +1, -1, +1, -1. Okay, be very careful about those charges. AP doesn't accept putting charges there. I'm going to be okay with it for a little while, but you should erase them when you're done. LiClO2 plus H2O. And that's balanced. And boy, if you're taking AP, whoopsie, don't erase everything. Don't throw the baby out with the bathwater there. If you're with AP, you need to go back and you need to erase those. So we want to get used to it. Use it as part of your work, but don't let charges like that be part of your final answer. They don't like them above, they don't like them below, and they definitely don't like them within. All right, aluminum hydroxide plus nitric acid. The positive aluminum is going to dance with the negative nitrate, but you've got to do it according to their individual charges. So I'll get aluminum nitrate plus water, and I would need a 3 here and a 3 here. Okay, and let's pretend we're AP, and let's go ahead and erase those charges we put up on top to help us out. Okay, those are our neutralization reactions. We're going to be doing an experiment, one of my favorites. You're finally getting into the experimental technique level that you'll be using for AP chemistry. All right, now titration is a technique where we're going to determine the unknown molarity of an acid or a base. All right, and what we do is we take a solution of known molarity, We're going to add it drop by drop to the other solution. We're going to use a burette. And we'll see one in the notes on the next page. Now, the solution is added until what is called the equivalence point is reached. This is the point when we have chemically equivalent amounts of our H plus and our OH minus. Okay? Now, once we've reached that equivalence point, we would say, well, I don't like that part, okay? Let me do it this way, all right? I don't like the way this is written here. We need a way to see that equivalence point. And we're dealing with clear and colorless acids and clear and colorless bases forming water, which is clear and colorless. So we need a way to show or indicate when we're done. And we use an indicator. An indicator changes color with pH. So we want an indicator that changes color at the pH as close as we can get to our equivalence point. Now, that point at which it changes color is called the end point. Now, of course, our goal is this. Our goal is that the end point is exactly equal to the equivalence point. We choose our indicators so that we get those as close as they can possibly be. And I don't know if we'll use phenolphthalein or bromthiamyl blue. It depends on what I decide to have us titrate. We might titrate acetic acid or we might titrate aspirin. We'll see. All right, so this is a picture. This would show the end point, and it's actually a little too pink. We want this to be as faint a pink as possible, so pink that you would be tempted to come up and ask me, Dr. Leggett, is this pink yet? And I'll say, I don't know. It's your experiment. But that's how faint you want it to be. So we would put our acid in here, we'd put our base of known concentration here, and we're going to put our indicator into here, and we're going to slowly, drop by drop, twist by twist, we'll twist it, swirl it, twist it, swirl it, twist it, swirl it, very slowly until this turns as faint a pink as possible. Okay? Now, once you're in pre-AP, we're going to use a pH probe where we would add base, measure the pH. Add base, measure the pH. And you would actually see a curve that looks like this. Okay? And halfway up is the equivalence point. Now, if we have a strong acid plus a strong base, the equivalence point is 7. If we have a weak acid with a strong base, it's going to be greater than 7. And that's typically what we do in the lab. And phenolphthalein turns pink at about pH 8. So it's perfect for the titration of a weak acid with a strong base. Now, if we have a polyprotic acid, many protons, which is what we do in pre-AP, that shows the first H plus being neutralized. That shows the second H plus being neutralized. And we've only had one group see the third because it is so not even that much. It's the equivalence point is barely a blip in the curve. So we've not really seen that third equivalence point. It would take probably 2 hours to titrate to that. But you would see for each H plus, so in H3PO4, for each H plus being neutralized, you would see that sharp rise in pH as you get the equivalence point. as you neutralize. Now, I'm going to do something. I'm hesitant to do it. I go back and forth on what I like better. But my AP students keep forgetting to put the OHs and the H pluses in this formula. It's really, in a sense, a formula that bypasses understanding. And so they keep messing it up. And so I'm going to go back to what we do best, and that's stoichiometry. This is easier. I'll be honest, it really is an easier formula to use, and if you use it, I'll give you credit. But I'm going to show you good old-fashioned stoichiometry. So we have calcium hydroxide plus 2HCl yields calcium chloride. Whoops, I didn't need that parentheses, sorry. Plus 2 waters. Okay. Now, we know the volume of this. You did this kind of a calculation in your homework for the last unit. We saw these. This is solution stoichiometry. Now, molarity means moles equal to 1 liter. If you write it as a double unit, it's easier to see it's a conversion factor. Now I have 25 milliliters, and I want to know what the molarity is. If you're solving for molarity, we're going to have to hop out of here and plug in our moles per liter. So let's go ahead and do this as a complete stoichiometry. And so step 1 will be the stoichiometry. Step 2 will be to plug into the formula. You start with your given, which is a volume. Molarity is a conversion factor. So I have 45.8 milliliters. I want to get rid of milliliters and go to liters. And this is of calcium hydroxide. You want to label that very carefully. Now I'll use my molarity. It's that many moles for every 1 liter. That's how I got my liters to cancel. Now I want to eliminate moles of calcium hydroxide and go to moles of HCl. And this tells me there's 2 moles of HCl for every 1 mole of calcium hydroxide. Okay, I've run out of room, so I'm going to hop down here, and then I'll just erase it for the second one. So when I did that mathematics, I got 0.0458 moles for every, we have to convert that to liters. And so my molarity was 1.83 molar. I'm telling you, it is more work than plugging and chugging into this formula we gave you. Hydroxide, calcium hydroxide has 2 OHs in it. HCl has 1 H plus in it. And then it's kind of like a voom voom. It's modified voom voom. I like it, and it's fine as long as you remember to put those mole ratios in there. All right, if you don't put the mole ratio, you can't get full credit. So that's the problem my AP students keep running into. All right, let's try this last one here, and then we'll have a little short video on acid rain, and we'll be done with this unit. So I have 2 H3PO4s. I'm going to write it as an already balanced reaction. SROH2 is going to yield strontium phosphate. Switch the positives with negatives so that you have new positives and negatives together. Okay. Now, that's my given for strontium hydroxide. I want my molarity of H3PO4, so I need my moles of H3PO4. Then I can divide it by my 0.50 liters. And I'm as good as golden. All I have to do is get to moles and then go moles to moles. So I'm going to go ahead and take a shortcut here. I'm going to convert 45 milliliters. I better take my shortcut correctly. I'm going to convert those 45 milliliters to 0.045 liters. Now I can multiply that by My molarity is 0.75 moles of strontium hydroxide for every 1 liter. That's my molarity. I'm using molarity as a conversion factor. My liters cancel. And then it's 3 moles of my H3PO4 for every, 2 moles. It's getting a little late at night for this old lady teacher of yours. 2 moles per 3 moles. Sorry, glanced at the wrong number. Glad I caught it. Otherwise, I'd have to give somebody a candy bar. Okay, and I got, when I did my algebra, 2.25 times 10 to the minus 2. So when I divided that out, I got 0.45 molar. All right, in the next video, we will just touch on acid rain and just link chemistry to the environmental effects that we deal with. So until our last video for this unit, this is signing off.